Can you check? Okay.
Okay, so starting over again. So basically what you're supposed to be seeing in this picture is a function f, which up to a constant factor and a constant shift is the same as the attractor A1 that I had in my lecture yesterday, as a function of a variable called w, which is literally the same as tau t, the variable I had yesterday. And what you're supposed to be seeing is that for different initial conditions, which are the blue lines here, you approach a single trajectory penciled out in magenta that is the attractor of the system. Now, what is basically, this is not sort of a model, if you want. So this is the actual sort of solution of this differential equation that I had, or version of the differential equation I had on the board yesterday. And what's also shown on the plot here are two lines here, one which is dashed in red and the other one is dashed in green. And what these are the first and second order truncation of the late time series that I sort of sent out. So yesterday I had a result where it said that the attractor at late times is given by, so A1 is given by -1 plus a term that sort of went as e to over s times 1 over tau t, again up to this constant factor and shift. That's essentially the red line in this plot here. Red dashed line in the plot. Essentially, it's Navier-Stokes. Yeah. The green line is second order truncation, so it will correspond to BRSSS.
And the constant that it goes to is ideal.
Exactly. So this, because of the different conventions, this function f here goes to plus 2/3, which is essentially the same as the -1 I had for the attractor A1. So the relation, if you want, so between f and a is that A1, I think, is 3f minus 3. I think that should work out. So the point to take is that, okay, this comes out from an actual calculation, and what I will sort of point out repeatedly, but I start here, is that the red dashed line is close to the magenta lines for values of w, in this case of around 1 or something like this. So it's actually very close to the attractor, not only in the very late time limits, sort of, but already starting at gradient strengths, which are order unity.
Can you remind what W was?
Yeah, W is the same as tau t in my plot yesterday.
So tau is larger than 1 over the temperature, which is the typical relaxation scale in the system. Then this
right. So we get to the actual sort of numerology, if you want, so after sort of showing a few points. These are more plots of these attractors, now in sort of slightly different systems. On the very left-hand side, we have the plot, which essentially corresponds to the one that was done, that was on the previous slide. So the plot in the sort of mock microscopic theory. But then there are two more panels in this plot here, the central panel, which is for kinetic theory in the relaxation time approximation, and on the right-hand side for n equals 4 super EMLs calculated via ADS-CFT. Now let's look at the central plot first. The thing that you should notice is that, again, here, the gray dots, these are sort of solutions of kinetic theory in the RTA, relaxation time approximation, using Boltzmann, using Bjorken symmetry. And what you find is that if you start from different initial conditions, you have the same overall qualitative feature, that there are trajectories that approach a single line or trajectory, which is penciled out in black here. So there's an attractor for the kinetic theory in the Boltzmann case too. And you have a similar feature in the sense that if you compare this to the series expansion at late times, which here is given in blue and orange, then you find that, again, the series expansion sort of comes close to the hydrodynamic attractor for values of tau t of order 1 or similar. On the right-hand side, now we have the case for n equals 4 super EMLs. And this case looks much more rich than the other two cases. However, it has, in principle, the same features. If you start from a different initial condition, then you're originally not on this curve, which is labeled attractor here, but you sort of approach the attractor curve not in a simple exponentially damped manner, but in an oscillatory manner. We will sort of later see that we can understand that to the fact that I said that this approach of initial conditions to the attractor is dominated by the non-hydrodynamic mode nature. So I explicitly showed that for this first left panel here, for this mock microscopic theory, the approach comes from this non-hydrodynamic mode, which has dispersion relation omega is minus I over tau. That's a single pole which sits at, which has no real part. And hence sort of the corresponding approach in real time is just purely damped exponential. That's why these curves sort of on the left-hand panel sort of nicely approach the attractor. In the case of N+4 super EMLs, the non-hydrodynamic mode nature of the system is given by quasi-normal modes, which have both the real and the imaginary part. So that means that there is exponentially damped behavior multiplying a cosine or a sine function. So you get oscillatory behavior, but nevertheless approach the attractor. There's a question. The difference simply comes from the fact that, okay, on the left-hand side, it really is not an actual microscopic theory. It's something we essentially wrote down. The right-hand side, N=4 super EMLs, okay, it's also not physically realized in nature, but it's a well-defined sort of quantum field theory, and it just has a spectrum that's richer than this mock microscopic theory that we wrote down.
So you also have the Boltzmann diagram we discussed, which looks like the left-hand side qualitative in terms of the approach to the attractor.
Right.
It doesn't have these oscillating parts. So where do the oscillations come from? That's studies there in the strong coupling movement that you don't have.
Right. So the question is, where does the difference come from between kinetic theory and in particular ADS-CFT? The difference comes from the fact that, well, so okay, in principle, Boltzmann would also have a non-vanishing real part of the mode because it has a branch cut. We'll talk about that in a moment. However, for Bjorken flow, you're essentially sitting at wave number k is 0. There's no spatial dynamics. And as such, the branch cut shrinks to a point which has no real part. And as a consequence, the approach to the attractor in the central panel is just purely exponentially damped. Whereas if you had an actual system with spatial dynamics, there would be oscillatory behavior. But we can't see it here because we sort of had a system that is homogeneous. So we've explicitly sort of taken that out. Oh yes, on the ADS side, we also consider Bjorken, but there, even at the k to 0 limit, there is a non-vanishing real part to the quasi-normal mode spectrum. You cannot get rid of it. The analytic structure is different. Let me maybe sort of defer I will talk about the analytic structure between these different sort of theories. Here, I really sort of want you to concentrate mostly on the fact, okay, these different systems have solutions that we can track, and there seem to be apparent attractors in all of these systems, which pretty much for all of these cases we have to find numerically. But they are there, and the approach to these attractor curves really sort of follows this pattern of these non-hydrodynamic modes that I've shown for this mock microscopic theory here on the left-hand side. But I will at least sort of discuss how you get that also for the other two theories. Question?
Just to understand, so what are the different sets of points in ADS vectors, different initial conditions?
Correct. Yeah. So all of these points basically sort of correspond to, you pick an initial condition for your energy density, and you solve your equations of motion, and then you follow the trajectory, and the different dots just give you how a single trajectory sort of evolves in time.
But this is ADS, so you pick some initial metric.
That is correct. For the ADS-CFT case, you have to sort of supply not only initial condition for the energy density on the boundary, but for all of the coloration functions. It's a particular sort of class of solutions.
Right.
Yes. Yes, and then you go solve. That's correct.
But then I'm confused because ADS is a strong coupling, right? It's an exact theoretical answer. I thought maybe it was minus independent from before from hearing various talks in the attractor, but what's insinuated is that maybe the attractor is a true behavior, say kinetic theory and whatever these are, whatever types of find this thing by conversion to the attractor. But then in case of ADS, you cannot say that the attractor is not correct and not ADS, right? Because the strong coupling is exactly right? So then what is the meaning of that?
Okay, so the question is whether what the meaning of the attractor is versus a particular solution to the equations of motion. Is that the question?
So I thought the meaning of the attractor was, and that's why
Right. So the question seems to be what the meaning of the attractor is versus the exact solutions to this field theory side. Yuri is absolutely correct in pointing out that in particular in the right-hand panel, but also in the other two panels, each of the trajectories that's traced out by these gray dots in particular are exact solutions within the field theory or kinetic theory in the RTA approximation or this mock microscopic theory RBSS. All of those are exact solution given one particular initial condition. Right. What the meaning of the attractor is that if you sort of wait a certain time, there's a particular initial condition to which all other trajectories are attracted to. So no matter where you start from, if you wait a certain time, which you can think of as some generalization of the relaxation time, you will end up on the black curve.
I wouldn't call it just the initial condition, because one of the ideas solution starts from the same initial condition, but then oscillates away from it before eventually converting.
No, it starts at different times.
No.
What are you referring to?
Well, I'm not going to go and point to it, but it's a curve that starts at time, at the earliest possible time, it starts at the same place where the attractor is. But then it deviates from it. So it's not the same initial condition.
So initial conditions are used in the broad sense that you're not only fixing the value of energy density, but you're fixing the whole correlation functions in this particular field theory. And if you start with the same field theory, but if you wanted so some higher order time derivative that's different from what the attractor tells you it should be, then you will initially sort of deviate. So initial conditions is used in the sense that you have to specify all sort of properties of your field theory.
Okay, so what you're saying is that even in ADS-CFT, you may be able to set initial conditions in the broad sense of the infinite power of correlation functions, but the system could just follow that solid line.
That is correct. Even in ADS-CFT, you can find initial conditions such that you just are on the black line. And in fact, this is how the black line is generated. Yeah. Okay. Thanks for sort of this discussion, because I think it's important to clarify what's going on. Yes.
Maybe I'm jumping the line, but because of this differential suppression gets multiplied by some power law, and the power law has some bigger parts, which I think also gives.
So the question is whether there is oscillatory behavior also in the Boltzmann equation. And so I'm not immediately aware to recall something like that, but I would be sort of interested in what that actually looks like. So I don't actively recall seeing that for Bjorken flow, but please educate me if I'm wrong afterwards. Yes.
Are the oscillator interactions between hydro and non-hydro modes?
The oscillations really sort of stem from the fact that the non-hydro modes have non-trivial dispersion relation. Of course, the full system will also have interactions between these modes, but at least, okay. Apparently, you can, after some time, so not at sort of at the very earliest times, but after some time, apparently the correlations or the interactions between different modes is weak enough such that you can actually track out just the sort of superposition of the individual modes and non-interacting as a very, very good approximation to what the attractor is doing. Yeah.
Can you please comment on the difference of the attractor and the values of the transport coefficients?
Yes. So basically, as with okay, all of these three cases are three kind of different microscopic theories. In particular, on the ADS-CFT side, the transport coefficients are fixed by the fact that you're studying n equals 4 super AMLs, which has one particular set of transport coefficients. These are the numbers that are sort of shown in the right upper panel. For the other cases, the kinetic theory and the RBSSS theory, there are transport coefficients in these theories, but we can basically dial them by hand. And these plots just show a particular choice of transport coefficients for these theories. These were mostly chosen for illustrative purposes rather than having some sort of deep meaning. Unless there are more questions, I would like to sort of simply sort of finish up with that picture by pointing out again that if you look at the series, late time series that is generated by sort of doing zeroth order hydro, first order hydro, and second order hydro. These are these curves here, which are red, blue, and orange. And what you should again sort of see is that in particular, the first and the second order hydro approximation, series approximation, are close to the exact attractor curve at sort of gradients tau t of order unity. Maybe sort of for further use, I will sort of use a particular sort of case. I will look at the left-hand panel. And the reason that I look at the left-hand panel is that for this case, the transport coefficient eta, so eta over S, which is the C eta coefficient here, was fixed to 1. So that means I will have an easier time doing my numerology when I talk about Knudsen numbers and mean free path. So for this case here, you see that the onset or the agreement between, in particular, Navier-Stokes, which is first order hydro, and the attractor happens at values of tau t of order 5 and larger. So I'll keep the number 5 in mind, okay? We'll use that later. There were also some questions earlier on in the lectures. What happens if you break some of these assumptions that you have a conformal system, or that you break sort of symmetries? So here are two examples of an attractor in a non-conformal system. So this is non-conformal kinetic theory with a mass, which breaks conformal symmetry. And here are exactly the quantities I discussed in my lecture, which is this A1 attractor as a function of gamma. And what you're supposed to be seeing is that these black lines here, which again are different initial conditions, different solutions, sort of are attracted to a region which is now not necessarily sort of measure 0, but may have some sort of non-extensive width. And then they follow sort of this curve as you go on and sort of go to weaker gradients. And just to sort of complete the picture, on the right-hand side, I mentioned this in passing. There is not only one attractor, but there's also a second attractor, A2. I didn't really define that. That's the attractor that measures, if you want, so the approach to the equilibrium equation of state as you take the gradients to be weak. And you can again sort of see from these black lines that start from different initial conditions that there seems to be attractor behavior also in this bulk sector, which is sort of something you wouldn't see in the conformal theory because the equation of state is always epsilon is 3p. Any questions on that?
What do you mean by approach to the equation of state?
So
The equation of state is, for me, something that characterizes the local equilibrium state, not the local equilibrium state. So how do you define an equation state for the local equilibrium?
Right. Yeah, I apologize that I didn't really sort of discuss this in too much detail. Really, what A2 measures is the sort of deviation from the effective pressure, meaning equilibrium plus bulk corrections, to just the equilibrium pressure.
Okay, so it's a measure for the bulk pressure.
Yes, in some sort of scaled variable sense. That's precisely what it is. Yes. Yeah.
So it's basically showing how bulk pressure is going.
And that there is attractor behavior also in this particular channel. Yes, that's what the right-hand side is supposed to be shown.
Whereas what you showed us yesterday have no bulk pressure, it only has shear.
Right, exactly.
Attractor behavior in both shear and bulk.
Exactly. So what I showed before were just for conformal systems where there was no bulk pressure. And the question arises, is that maybe a coincidence that you only get attractors in conformal systems? The right-hand side shows no, there really is attractor behavior even in the bulk sector. And that is what is shown in this right-hand plot. Finally, let me just mention, no, not finally, there's one more thing I want to say. I also said that you can look for attractor behavior now away from Bjorken symmetry. So this here is a plot that is showing you the evolution in the A1 gamma attractor plane for a system that's conformal, but is initialized as a two-dimensional sort of system with arbitrary transverse motion. So it is something that is akin to a heavy ion collision that's expanding in Bjorken scaling in the longitudinal direction, but has arbitrary sort of fluctuations in the transverse plane. And every line here is basically you pick some particular point in this sort of transverse space here, you set an initial condition, and then just follow its trajectory in the A1 gamma plane. So what happens is that you start on the far upper left, and you basically follow the lines to the bottom right, and this evolution at comparatively early times is something that you can understand from the fact that at early times, the system evolution is essentially just one-dimensional. It's almost Bjorken-like. So you expect the result to be close to the Bjorken flow attractor that I showed before. And indeed, that's kind of the case because if you look at the line which is labeled Navier-Stokes, that was a good proxy of the Bjorken flow attractor for early times. But at late times, what happens is the system sort of expands fully three-dimensionally. So the curves actually turn around. They turn around and come back, and they sort of follow an apparent attractor behavior that sort of goes back up to the upper left, which is now labeled as an orange region, and basically sort of seems to be going to almost a sort of free streaming limit at late times. Okay. What is R? It's supposed to be, it's gamma. That's the scaling variable that are defined as my. No, it doesn't oscillate in size. No, gamma.
Oh, it's a scaling variable from the left.
Exactly. Yes, it's the scaling variable defined that I was looking for. Yes. So it's a not completely trivial expression that involves the shear stress and the bulk stress, or the shear sort of motion and the bulk motion combined in the supervolume.
Yellow attractor is free streaming.
The question is if the yellow attractor is the free streaming attractor. The answer is I don't know. Yeah. So maybe. Okay, finally, I wanted to say that, yes.
This kind of behavior is just in your but if you really delay or less,
Right. Yeah. So the comment is that something like this can be sort of seen also if you don't do fully three-dimensional dynamics, but use only Bjorken, but you sort of engineer your interaction rates to sort of suddenly decrease as the longitudinal sort of expansion sort of takes its place. And then you can sort of show maybe that you sort of find the free streaming attractor in the late time limit. And this is sort of also something that I want to sort of say. I have one example here to just say that this business of finding and looking for attractor behavior is an active research area. So this is a paper that is from the local group from just a few months ago. And essentially what it's showing is that there is sort of different sort of systems where one can look for these attractors. And I think all I wanted to say is that sort of this subject is certainly far from complete or finished. So it's an active research area. And I think it deserves maybe sort of more attention in the future. I will want to pause here for a moment and see whether there are more questions on the slides, because then I want to go back and sort of finish up with some of the things I promised last lecture, and finally sort of get to sort of new topics at the last part of the lecture, which includes then also tomorrow. Yeah, you're.
Sorry, sort of more philosophical question, and I'm asking only because I think you're about to move on from the attractors. So why should we be excited about the attractors? I would get excited, more excited if it wasn't in fact the a solution that would kind of begin with the sense. So kinetics theory and this and that. But then it seems like what you told me a few minutes ago is the exact solution only making for specific initial conditions, which may or may not be realized.
Right. So the question is, why should we be excited about attractors? So I'll tell you a few reasons why that would be exciting, but let me sort of give you the sort of answer that I'll sort of expand on as soon as I sort of finish with my slides and go back to the blackboard. One of the reasons you could be excited about is that the attractor sort of is the curve on which basically all initial trajectories, all initial conditions in your system will decay to, and they will decay to in general, or in particular, exponentially quickly. So what that means is that after some time, and the time here sort of is something that I will argue is shorter than what you would have expected, you get to a curve which sort of all trajectories have to be on. And furthermore, this curve sort of happens to be such that if you were to just take your series expansion of hydrodynamics, or your gradient expansion, and you truncate it at low order, It is a divergent series, as I will argue, but you truncate it at low order. You get these curves here, which are colored blue and orange. And what you find is that these curves are close to where the system dynamics has to end up at gradients which are not that small. And I'll give you the numbers for this. So that's one reason to be excited about it, because it means that if you didn't know anything about the attractor, you were just solving Navier-Stokes, you would actually capture the exact system dynamics, even for systems where the gradients are sizable. That's why it's exciting to talk about attractors. One reason. And I'll give you another reason as I sort of go on. More questions? Okay, then I will sort of switch back to Blackboard. And I probably have to change. Do you know how to change back?
Okay, yeah. I think now we are set.
Okay, very good. So it seems like I can continue now. Sorry for the disruption. Okay, so basically, just to sort of reiterate that point here. So there is what I would call an old school criterion for the applicability of hydro. And I will sort of put this under quote because different people sort of may have. Okay. That is simply that if you have a system that has a local mean free path lambda alpha mp over the system size, that sort of ratio has to be much less than 1. That's if you open a textbook on fluid dynamics, that's sort of the criterion that people have been using for decades, essentially. So essentially, we can sort of see whether this sort of new attractor criterion sort of offers something different. The attractor criterion sort of says that hydro, in particular Navier-Stokes, first order hydro, is close to the exact sort of system evolution for times when the sort of this ratio tau t was larger or equal than 5. So remember the 5 that I sort of told you to memorize. So how does this go together with this lambda mean free path? Well, I have to tell you what this mean free path for these relativistic systems is. That is basically just the ratio between the shear viscosity and the enthalpy. So we can again use basic thermodynamics to sort of rewrite this as E of S times T. And the sort of 5 that I sort of pointed out to you was for a particular sort of plot where I said that this ratio E of S was chosen to be 1. So that's easy for me now to say, okay, this ratio E of S is here is 1 in order to sort of do the numerology that I want to sort of embark on. So lambda mean free path is then sort of for E of S C plus 1. This means that lambda mean free path over the system size, or yeah, I should say the system size for a system that's Bjorken expanding in one direction is just the time tau. Okay? So after some time tau, the system is of size tau. That's a question.
This criterion for tau t being greater than the factor of 5 is specifically for Bjorken or in general?
So for the plots that I showed you, this was for Bjorken, and you can actually figure out that it's actually independent of the plot that I showed you. I said that this is one plot where I see there is 1. You can actually do the ratios for the other plots as well. You find the same numbers. So yes, it's for Bjorken. You'll find that sort of it also holds true for systems. For what I showed is just for Bjorken. Let's just put it. So then we find that this ratio, lambda mean free path over the system size, if we plug in these two numbers, we find that we have 1 over system size is tau times t, and that because we know that
this is a good criterion. This has to be less or equal than 0.2. And if you sort of compare these numbers, you immediately remark that, okay, we have certainly found some improvement over the textbook, old school textbook criterion, because oftentimes it has to be much, much less than 1, meaning that, so we usually sort of say, okay, maybe the mean free path has to be 1/1000th of the system size in order to sort of use fluid dynamics. Well, in the system that we can actually sort of look at these attractors, we find that the mean free path has to be more like a factor of 5 smaller than the system size. And Navier-Stokes is a good description of what the system is actually doing. In order to sort of show what this means for, in particular, heavy ion collisions, so for nuclear collisions, let's just put in numbers. What do we have? It means that this criterion has to be smaller than 0.2. So if the lambda over L has to be less than smaller than 0.2, we can sort of put this around and say, okay, L then has to be bigger than 5 times the mean free path. The mean free path again is given by this formula here, eta over st. So for QCD, we believe that eta over s is in the ballpark of about 0.1. For nuclear units, the temperature is in the order of 200 MeV, lambda QCD, which is 1 inverse Fermi. So you put this in, and you find that basically you eta over s is 0.1. So basically you find that this has to be larger or equal than 0.5 Fermi. So we claim that this shows that Hydro works for the low order truncations of hydrodynamics. Navier-Stokes works for basically systems that have half a Fermi size extents. So in particular, this means that Hydro works for systems that are created in proton-lead collisions, and even proton-proton collisions. Just to sort of say, the size of the proton is about 1 Fermi. So if you collide 2 protons, you get a size also on the order of a Fermi. So clearly this is sort of maybe not sort of quantum leap forward, but it certainly is something that brought us a long way from the old textbook criterion that would have said that, okay, really you need system sizes that are much, much bigger than the mean free path in order to use a lower truncation of hydrogen. Yeah.
When you write lambda mean free path, eta over xt, the second like eta over xt,
Yes.
analyze.
No, I do not. So basically, these are sort of treated in the sense that I said earlier. So really, sort of what is appearing here is this ratio here, and you should think of okay. So the energy density is the energy density out of equilibrium. That's fine. And really, the P here is the P that is not in equilibrium, but it fulfills an equation of state as an equilibrium, because all the rest sort of was put into these extra sort of bulk degree of freedom, the pi, capital Pi. So in that sense, it's a pseudo entropy and it's a pseudo temperature. But nevertheless, these fulfill the equilibrium relations. Yes, I'm using the same sort of as the usual sort of thermodynamic relations. That's right. Yes. So and I would argue that, okay, so essentially in some sense, this sort of goes at least some way along the lines of saying that, okay, this kind of explains or goes towards explaining this unreasonable success of hydrodynamics in very small systems which are not much larger than the mean free path of the particles or constituents themselves.
Your
Yes.
estimate was kind of conservative because of 200 MeV temperature. characterizes more the end of the collision rather than the beginning of that.
That's correct. That's correct.
Maybe a factor 2.5 higher.
That's correct. So this is a conservative estimate, but I will say that I think we can do even much better than this. And I will talk about it.
Sorry, I missed it.
Yeah.
Justify the lambda over L less than 0.2, you estimated A over S to be 1.
Right. So this was just for the plot. And I said it's not, it doesn't, so that's the plot where I took the numbers from, but you can take also the other plots where theta of S was not 1 and you find the same ratio. It's just that so that the C eta is different, but also the value of plot T is also different. And then the ratio between the two of them that comes out to be 0.2, regardless of the value of the source. Sorry, I was a bit quick. So I will argue we can do better than this. Let me see. So today I started a quarter to 1, which means that I have 3/4 of an hour. Okay, good.
Yeah.
Very good, very good. Okay. Good. So I think what I really like to do is I want to really sort of get to the central point of these lectures. There's something that I promised to do yesterday, which was that I want to show you how you do a Borel transform if you have a pole on the real axis. I still want to get to this, but if there's something I want to cut from my lecture, it's probably this, because I consider it more for technical details than the others. So I'll defer that to the end of today's lecture if I get to it. So I want to sort of continue with the line of thought that I've outlined here for now. Okay. Okay, so what's the big picture? So it seems that for all the theories that we can actually sort of treat, in the sense that we sort of can solve them exactly, there are, for instance, a microscopic theory that we have a handle on, or there are some sort of thing that we construct that we have a handle on, like a ordinary differential equation. We can study, in particular, the response of, or we can sort of, we can make plots of the scaling quantities, for instance, A1 as a function of gamma. And we really very generally sort of find this feature that we have one particular curve that is special in the sense that it's one particular solution, exact solution of the equations of motion. You can start from different initial conditions, which sort of will end up somewhere else, but you basically sort of have some form of behavior that sort of is maybe oscillatory, but eventually sort of goes onto this single curve. So that's the case for at least the 3 cases that I've showed you, RDRSS, kinetic theory, n equals 4 super mills. And it's likely to be true in sort of more general context, and people are still exploring this. So, it seems that systems possess these kind of attractors, and the sort of leave it here as a statement. There's no proof that this has to be true for all systems, but it's certainly true for pretty much all the systems that we've looked at, where we actually have handles. And the second thing is that the approach to these attractors follow the decay of non-hydro modes. What does that mean? Well, it means that, let me sort of show you what it means. If I start my system with some particular initial condition, let me sort of prepare it such that I have some sort of source S of x, which sort of characterizes the space-time structure of my initial condition. then I can sort of use that to calculate the response of the system in x and t, at least to linear approximation as a Fourier transform of the associated two-point function of the energy momentum coupled to that source now in Fourier space. So what that means is that if this Green's function, omega and k, has singularities in the complex plane, these complex plane singularities will determine the features of what my response looks like. Okay? So for the case of RSSS, the singularities of the Green's function g look like this. So I plot the real part of omega here, the imaginary part of omega there, and depending on the channel, let's sort of talk about the sound channel. We have in general sort of two modes sitting at plus and minus CSK plus minus the damping rate. These are the usual sound poles. And then in addition, we have the non-hydrodynamic mode sitting at -1 over tau pi. This is omega is plus minus CSK minus I gamma k squared. So if that's the structure of the Green's function, if I calculate this integral here by, so I'm supposed to be integrating omega from -infinity to +infinity. So I'm integrating along the real axis. I can evaluate the integral by closing the contour below, and I'll pick up all the structures. In this case, it's single poles. The single poles will sort of give me values of this omega here evaluated at these various poles. So what I will find is that this will be equal to e to the sum over all poles. Oh, let me do more. So I will find a structure that is e to the minus I CSK T, and actually there will be a plus minus because I will have two of those, plus minus CSK minus gamma k squared T, from the fact that it has imaginary part minus k plus ikx times the source times residues. And then in addition, I will get a contribution from this guy here, plus e to the minus t over all pi plus ikx, also times s of k and residues. How does that look like in real time? Well, it says the response is given by sort of the sum of all modes in the system. Okay, so here I have two modes, the two sound modes, and I would claim that these two sound modes really are the attractor. This is the single curve here, which is well behaved for all gammas. And then in addition, I have this piece here, which implies exponentially quick decays at late times. And this is just the exponential approach. In this case, as I had oscillatory behavior, this is the exponential approach to the attractor curve. So there's a one-to-one mapping between the analytic structure of your two-point function calculated in equilibrium to the fully out of equilibrium response of the system, in the sense that there is one particular curve which is the generalized hydrodynamic behavior of the system, where hydrodynamics has nothing to do with Navier slopes anymore. It just says that there are two poles in the Green's function that, if they are there, determine the presence of an attractor, plus other stuff that sort of characterizes how initial conditions decay or how the system loses its memory of initial conditions. This is the simplest case that we looked at. Of course, you can look at more complicated cases. Yes, the question is if
That's why
the,
the attractor is dominant.
right. So the question is if the things that are closer to the real axis, whether those sort of are more long-lived than others. And yes, the answer is yes. So the distance from the real axis gives you essentially the sort of size of the damping, the inverse lifetime of the mode. And yes, if the hydro modes are the ones that are closer to the real axis, the attractor will be dominant feature. And we'll talk about what happens if that reverses, because that's where really sort of interesting stuff happens. Before I sort of go there, let me sort of remind you that the similar picture applies to other sort of microscopic theories where we know this analytic structure of the two-point function. Write down the same thing for kinetic theory, RTA, again, real part of omega, imaginary part of omega. Again, looking at the sound channel, there are two sound poles, and I think I even want to make this more quantitative eventually, but the sort of non-hydrodynamic mode feature of this is that there is a branch cut sitting at omega is minus I over tau r, where tau r is now the relaxation time that we put in the collision current of the relaxation time approximation. And this branch cut stretches from minus k to plus k along the real axis. To complete the picture, you can also draw the corresponding diagram for the case of n equals 4 superangles. Real part of omega, imaginary part of omega. So again, if you look in the sound channel, you have two sound poles. And in addition to that, n equals 4 superangles has this Christmas tree structure of quasi-normal mode of the black hole. So usually look like this. They go off all the way to infinity. So we can think of an infinitely large tree. It sort of has this Christmas tree shape. These ones are hydrodynamic poles. All the rest are so-called non-hydrodynamic modes of a black hole. This is how you calculate them. We know these are real. Okay, so these have been observed in astrophysical black holes from gravitational wave signals. So we know that at least these two exist. So they are real features of physical black holes. This calculation, of course, was done with 5-dimensional black holes, which you can't directly observe. But nevertheless, the idea is that if we just plug this Green's function into here, we like close the contour. Now we get contributions from sound poles plus all these other guys. And these other guys have non-vanishing real part, okay, even for vanishing wave number. So if you plug it in here, you see that if the real part of omega is non-vanishing, you get e to the I something. E to the I something is a cosine or a sine. That's the reason you get this oscillatory behavior as you approach the attractor curve, which again I would argue is given by just the sound poles. So I would argue that we have a fairly good, at least qualitative understanding of what's going on. Okay? And it only requires us to sort of calculate the structure of the two-point correlator in equilibrium of the theory. If we know this, I would argue we know the features of sort of the system dynamics, even in non-equilibrium situations. Now, unfortunately, we don't know the two-point Green's function analytic structure in QCD, but it would be an interesting challenge to at least try to make some progress.
Sorry, can you say again?
Yes.
Where did the observations come from the...
Oh, yes.
So this guy here is approximately given by omega is 1. This is easy. Minus 1 plus I times 1, approximately. If you plug this in here, you get a term that's e to the minus t times I, and then there's another one which is just minus. So this is plus t, and there's just another one which is just this guy here. The second one is just exponential damping,
and the first one is cosine gt and or sine gt.
So the fact that you have two non-hydrodynamic poles, the two leading non-hydrodynamic poles with a fixed value of k, this is what gives you the observation. Over there it has k to 0.
Yes.
And over there you have a continuous distribution, and that then you don't.
Correct. Correct. Yes. And what I was saying earlier is that this is the structure of kinetic theory in the RTA approximation for arbitrary k in some range. If you do Bjorken, you essentially have a homogeneous volume, so there's no non-vanishing wave number. It's wave number k is 0. And I said this branch cut extends from minus k to k. If you send k to 0, it becomes a single pole that really looks like that one. So that's why the plots that I showed you in Bjorken for kinetic RTA and this RBSS theory look qualitatively the same. Well, it's because we sort of have a very special symmetry that we used in generating these plots. And then because for superunions looks different even in K, even in Bjorken, the K is 0.
So the quasi-normal mode is the usual radius structure.
So in this case, the quasi-normal modes that you want to calculate is that of a black brane in radius 5. Because that's the one corresponds to equilibrium constant T on the boundary. Yes. So basically the idea is that I was going to do some of this, but okay. Yeah, it's fine. Let me just sort of answer the question. So basically, in ADS-CFT, and I'll talk more about this probably tomorrow. You have your boundary, which is in cos B4, and then you add a fifth dimension. And then in order to study equilibrium properties on this boundary here, what you put in is a black brane, which is just a sheet, has a non-compact horizon in the fifth dimension, at a finite distance, which is proportionate to the temperature of the system. Inverse proportional to the temperature of the system. That's a black brane here.
That's why the frequencies are the same.
Well, they are not exactly this. They are approximated this. Okay? There are numbers that you can calculate that people have calculated.
But why do you make the black brane and aluminum principal one in the ADS Schwarzschild?
If you do ADS Schwarzschild, the issue is that basically that will fall into the bulk. So it will not be stable, it will be corresponding to an expanding solution on the boundary. It's not equilibrium. Unless you go to global ADS5, which is a different story.
Right on the right, and it's been equilibrium. So if it's regardless of the normal mode, you just solve the whatever scalar, Daniel, whatever position independent of the method.
How about I show you how you get to these modes tomorrow?
Okay.
Let's do it tomorrow because I wanted to do that anyways. And we can do cosine numbers. It's fairly straightforward, all things considered. Yeah. Good. So that's sort of part of the message that I wanted to bring to you. In some sense, we can sort of see what's going on if we sort of essentially push this picture a little further. Okay. So let me sort of concentrate on the case of kinetic theory simply because there the calculation sort of can be really sort of understood in very, very great detail. All of the other things have similar sort of properties, which I can talk about, but let me start focus on kinetic. So what I showed you here was a particular plot of this Green's function, but I didn't say what value of parameters I used to sort of draw this line, and I used KTR is 1 or something like this. Okay. You can sort of ask, well, what happens if you sort of change the corresponding scale? Well, you could also sort of say, I can tell you that if you choose values of KTR, which is smaller than 1, 0.1 or something like this, the feature is qualitatively the same. It just means you're lowering the value of K in your approximation. And that means that these poles will move closer to the origin. Remember, these are the sound poles are plus minus CS K minus I gamma K squared plus higher order corrections. So as you make K smaller, these move closer to the origin, they become closer to original Navier-Stokes. If you go the other way, R small. If you go the other way, you make K to R larger. These modes move away from the real axis, and they become
quite unlike this simple Navier-Stokes formulation. They're still there. They're given as a solution of the corresponding equation. You can even write some of them in some form that involves nothing more special than arctangents, hyperbolics, and things like that. But they sort of move. They move downstairs, and eventually, if k to r gets large enough, they actually sort of, I think draw it very well, they actually sort of go and they fall through the branch cut. Okay? The branch cut is the branch cut singularity on the first Riemann sheet. And what these poles do, as you increase k, they go on the next Riemann sheet. Okay? They just disappear from your principal Riemann sheet. So for k to r bigger than some critical value, correct? Which for this particular case happens to be 4.53313, and so on and so forth. The poles, the sound poles, are no longer there on your principal Riemann sheet. Some people have objected to this view, and that's perfectly fine because it turns out that where you place the branch cut is a convention rather than sort of a feature. So I could have put the branch cut such that there are two branch cuts that go out, in which case my poles would not have gone to the next Riemann sheet. They would just have sort of continued along this line. However, what is universal is that above this critical value here, the singularity of the Green's function closest to the real axis, the mode with the larger lifetime, is now not the hydrodynamic mode. It's the non-hydrodynamic mode. And when that happens, the feature of the system response, this delta t, really sort of changes qualitatively. Okay? How is it possible? Well, it's possible because these are simple poles. So if you stick them in here, you get essentially exponential or cosines. But if the branch cut is the dominant feature, if you stick it in here, you get a power law. Okay? So then suddenly your behavior of your energy momentum tensor really is unlike hydrodynamics. It's something really different. You can see it. You can make a plot, and you see, okay, this is no longer exponential. It has a power law tail. I have lost the hydrodynamic attractor. So for this case here, hydro has broken down. You can calculate the precise point where it's actually broken. You can not only do this in kinetic theory, you can do it in other theories as well. You can do it in inverse force of AMLs. That the story is sort of kind of interesting. So you can sort of either sort of look at just pure n equals 4 superambulars in the infinite coupling limit and take k larger, in which case you'll have to think that these poles just move down, and at some point they move below the first non-vanishing, non-hydrodynamic Casanova mode. Or even more interestingly, you can include finite coupling corrections to the holographic sort of theory. Then you don't really have n equals 4 superambulars at infinite coupling anymore. You have some finite coupling corrections. If you do that, what happens is that, as my friend Andres Bernes likes to say, you get poles that are raising up from hell. Okay? You have poles that come in from here, from infinity, and they move up. Okay? And they move up, and at some point, these basically sort of move in, and at some point, these two poles sort of run into each other, and they annihilate. It's a very dramatic feature, and Andre has written beautiful papers about this. And while this sort of precise sort of mechanism is completely different in kinetic theory in n equals 4 superambulars, the upshot is the same. There is a critical value of the wave number, critical in sense of in units of the coupling, at which hydrodynamics completely and utterly breaks them. So I think the picture, at least in my mind, that we have from a fluid dynamics point of view in the 21st century is sort of captured by what I call the central lemma of fluid dynamics. And it started out as a joke, but I'll sort of write it down anyways. Here it is. It basically says that Hydrodynamics. Offers a valid and accurate description of the dynamics of the expectation value of the energy momentum tensor in the full theory. As long as non-hydro modes can be neglected. And there are a few things that I can explain about this. Okay. First of all, fluid dynamics here doesn't mean Navier-Stokes. It does not mean second order hydro. It means that there is some sort of mode, like a sound mode, that exists in a general sense, if you want. So there is an attractor. And the attractor is such that its lifetime, the lifetime of these modes is longer than all the rest that you have in your theory. Okay? If you have a realistic theory, I think you could argue that in any really realistic quantum field theory, if there are hydrodynamic modes, there are also other modes in the system. And as long as I can neglect these other modes in the system and just concentrate on the hydro modes, I will have a fluid dynamic response. Sounds like a trivial statement, right? I mean, basically says that, okay, if you have hydro, you have hydro. In a sense, it is. But I think it sort of is progress in the sense that, first of all, it means that since we're not talking about the lifetime of these modes, we can really sort of forget about all these sort of old definitions that say that hydrodynamics is a near equilibrium sort of limit. These modes exist perfectly fine out of equilibrium. We don't have any issues. I mean, they are either there or they are not, but there's nothing that ever says that we have to be close to equilibrium in order to sort of make this effective field theory sort of setting. And secondly, if you sort of talk about the Paulson swing functions, it gives us a quantitative way to calculate when hydrodynamics really has broken down. Okay, so we can calculate the precise critical wave number at which sort of the system reverses and the response becomes purely non-hydrodynamic mode-like. So I think that's, if you want to sort of what this statement is supposed to be.
I'll pause here briefly to see if that doesn't.
Okay. Yes.
Can I phrase this practically in the following steps? Just kind of avoid phrasing. When you start with some initial condition, and as long as the deviations from the attractor so decay faster than the evolution of the system as a whole, so that the attractor ends up dominating most of the dynamics of the dynamics. And it doesn't have to happen, the approach to the attractor doesn't have to happen where it's sort of Stewart or Navier-Stokes gets good. It can happen in a powerful equilibrium situation where it's not really a kind of far away from the attractor.
Right. Yes. Yeah, I would completely agree with the statement that this means that as long as there is an attractor and the non-hydrodynamic modes sort of decay faster than the sort of expansion or gradients of the system, then you have a hydrodynamic behavior, and that need not be the point where this residue of Navier-Stokes or any of the other truncations are actually good approximations of the system. So in this sense, this is what I meant when I said we can actually do much better than this sort of criterion where we said that lambda over L needs to be smaller or equal than 0.2. That was the criterion for Navier-Stokes to be good. So now, really sort of it is the question, what is the competition between between sort of hydro and non-hydro modes. And that, of course, sort of, if you want to by construction, pushes you much further out of equilibrium. You can sort of ask, well, what is sort of, if you want to sort of put in numbers, how far can we actually push it? And if I find my page that has that, we can sort of try to sort of see what that does. So let me sort of plot an answer to this question in the following sense. I'm going to plot K critical, the wave number, the critical wave number at which the lifetime of the hydro mode is exactly equal to the first non-hydrodynamic mode singularity, divided by the temperature, as a function of some coupling. And this coupling here is a tooth coupling. So think of this as being sort of G squared N in Young-Mills or something like this. And just as a reminder, if you want to sort of use this for QCD, what you would have to do is you would have to pick N is 3 for QCD having 3 colors, and G squared is sort of the one that corresponds to alpha S on the order of 0.3. So numerology, you get something on the order of, I think, 10 or so for QCD. And so let me sort of put some units here. Here is 6, I think here is 7 or something like this. A very weak coupling, lambda very small. What I did was that I sort of used, that I said, okay, the system is maybe well approximated by kinetic field. You might sort of object to this, but it's some weak coupling description. And you get a curve that sort of comes out from exactly these numbers that I showed you before, where we had this sort of overlap between these two modes. And a very strong coupling, we can sort of use ADS-CFT, starting at lambda is infinity and going down by sort of including finite coupling corrections. And what you find is that there is a formula that sort of is loosely saying that Kc over T is approximately, oh, why don't I give you the formula? Pi T over 4 times the logarithm of 7 lambda to the 3 halves divided by 1 plus 105 lambda to the minus 3 halves. I hope this is right. So check it. 1609 02820. I think that the actual formula is there. And this is not coming from my work. This is really coming from Andrei Starinetz's group, who did the actual N equals 4 super Young-Mills calculation. And I just sort of basically fit it there. 1 plus 105 lambda to the minus 3. Numerator, 7 lambda to the 3 halves. Yes, 7. And this is a fit to the actual data that they generated. Anyways, it turns out that you can sort of nicely try to connect this curve and you get sort of a smooth curve behavior. And if you sort of want to read off numbers here for QCD and you sort of have some sort of error bar here, you get something that says for QCD you expect this to be in the range sort of 4 to 7. Okay? So this is sort of the ballpark for the critical value of the wave number at which you expect hydrodynamics to break down in QCD. So then we can play the same games. So we can sort of say, okay, Kc over T is, I don't think I sort of know what I've plugged in here. Oh, it shouldn't be too hard. So, so if this is about 5, then this means that Kc is about 5 times T. So that means that this is basically about 1 GeV. So if you sort of invert this, this would mean that the system size, which is sort of Kc to the minus 1, is of order 0.2 femtometers, which would be the scale at which hydrodynamics should be breaking down. Again, this is kind of a conservative estimate in the sense that I plugged in T being 0.2 GeV here. If you wanted to do heavy ion collisions, in particular if you want to do proton-proton collisions, the temperature is actually quite large.
It's much larger than this 0.2. So you get the values of the system size, which are much, much smaller than this 0.2. And it basically leads to sort of farther afield. The main point being that, okay, so I think you can sort of draw a fairly well-suited argument that even in systems as small as protein-protein collisions, you generally would expect hydrodynamic behavior simply based on these estimates.
These hydrodynamics can really resolve equilibrium structure for
Yeah, correct. So basically, this is what, yeah, it's right. It's basically sort of saying that you should be able to sort of treat individual hotspots inside the proton using fluid dynamics. Yes, that's correct. Right. Right. So it is based on linear response in the sense that you're calculating the 2-point Green's function. And yes, there would be 3-point functions that would contribute to this. The literature on 3-point functions in these systems is not very rich. Oh, thank you. Very good. Yeah. So it's arbitrary k, but linear in fluctuations. So what I mean by this is that your fields, the energy momentum tensor, you only sort of take the energy momentum tensor response to be small, but k can be arbitrary. So this is exact for all k, but it's approximation in the response being linear in the fields. It's a different kind of linear. It's basically saying that in order to sort of calculate the response of a system, I can use its 2-point function and forget about higher point correlation functions. That's what it's.
You have more graph each other. So right now you have 2 by 2 scattering or reflection in the system, but if you have more and more social distance resolutions, then you have more.
Right. Right. So okay. Let me say that this is different from saying that you have 2-point interactions. So you're not expanding in 2-body interaction subject. This is all of this is many-body.
Yeah, well, I think that's the mode. Like you have way deeper. In passive or in way.
I think we should sort of discuss this in private afterwards, because so really sort of what's done here is that you're sort of taking 2-point correlation functions of many-body objects, energy momentum tensor in a many-body system. I'm not confident that this can be mapped into sort of a wave expansion in a similar, simple manner, but I'd be happy to learn more if you have some deeper insights into this. So it's linear in the sense that we are neglecting higher point correlation functions, but it's exact in terms of k. Okay? So k is not restricted to be small or large. And in particular, we can do this at infinite coupling. So it's not a small coupling expansion or a large coupling expansion. So these two parameters are not taken to be in any sort of corner phase space. Really what they're doing to calculate the response here is the linear response. And let me just sort of reiterate that when we then sort of do fully nonlinear fluid dynamics, we are taking all the nonlinearities. And what we find is that the response is given by these linear sort of correlation functions, just suitably sort of rescaled to the expanding system. So this was this trick where I said that we have the non-hydrodynamic mode in RPRSSS, which is just 1 over 4 pi. But in the expanding system, this is equal to minus I over 4 pi t, all to the minus 1/3. And then the response is given by e to the minus integral between tau of 1. Then you have a fully nonlinear system, but it's still governed by this minus I over 4 pi that you got from the linear response alarm equilibrium. Why this works, I can't tell you. I don't think I know this, but it works. Okay, I have 5 minutes left or something. Let's see if there are more questions.
Yeah, so I mean, one thing that I could at least try to do in this, to use this sort of last 5 minutes, is that I could quickly sort of explain how this ambiguity with these real poles on the real axis in Boyle transformation sort of gets handled. Okay.
Very good.
So back to Borel summations. So back when I was discussing this RBRSF theory, I said that there is an expansion for this A1 quantity, and sort of it looks like this. You can do a late time series expansion of this all e squared plus and so on equal to some n in 0 to infinity alpha n over alpha to the n. And it so happens that if you do this around for a Bjorken system with Bjorken symmetry, then in all of the systems that have been sort of analyzed, this sort of goes essentially like n factorial at large n. I mean the coefficient alpha n in the series. Okay. That typically is a hallmark of a divergent series. As a side comment, let me just briefly remind you that you can kind of understand this divergence, or the divergence in the coefficient, simply by counting the number of gradient terms that you can write down. So remember that at T0, the energy momentum tensor at 0th order hydrodynamics had 2 terms. At first order, we also had 2 terms. At second order, we had 9 terms. At third order, we had 68 terms. That's if we count all the possible nonlinear combinations of gradients that you can write down, independent ones. However, if you did linear hydrodynamics, meaning that you only sort of allowed sort of linear terms in the fields to contribute to the energy momentum tensor, you don't get that many structures because you don't have nonlinear combinations that you can write down. So fully nonlinear, you expect P mu n to go as n factorial for large n, but linearly, you sort of expect P mu n to go less than factorially, maybe quadratically or with a higher power, but typically not exponential. Okay? And that means that if the number of terms grow only as a power, and all of these coefficients are order 1, then they would not sort of give you this 1 over n factorial behavior. They would actually sort of be a convergent series. So expect that linear hydrodynamics has a finite radius of convergence. Nonlinear hydrodynamics has no finite radius of convergence. It's a divergence. That said, we can now sort of take this divergent series here. We can try to do a Borel summation of this A as a function of tau t, which is defined as alpha n over tau t dn 1 over n factorial. In practice, we never have these up to infinity. We have some finite, but maybe large number n of these terms. So it's hard to sort of do the resummation in practice. However, what you can do is you can do some sort of Pade approximant of this series, a linear Pade, or sort of a symmetric Pade with the same number of terms in the numerator and denominator, such that its series expansion matches the series that you calculated up to the power or the number of terms that you actually have. You Pade this, you get a function that you then analytically continue in the whole space. So again, recall that we did this, and we said, okay, maybe we get a function like 1 over 1 plus x, This has a finite range of conversions, but you just analytically continue it in the whole complex X plane in order to do the inverse product. That's the same thing. For the case of, so let me now, okay, how do I call this? Okay, this is slightly awkward, but let me sort of define omega to be 1 over tau t. No, this is not right. This is right. So, then basically what this is that I can write this as omega to the n, and then I can talk about this complex omega plane here, which is sort of not exactly the same, omega was a bad, not the same as the complex plane I was talking about before. In particular, it's flipped by 90 degrees, but it's just here, it's just the complex plane that we have here for this Tabet approximant. And what you find for the case of our BRSSS, which is the theory that I talked about in the last lecture, you find that the structure is such that it has a pole on the positive real axis, and then a dense series of poles right afterwards, which is meant to approximate the branch cut along the positive real axis. So this is a problem because we would like to sort of do the inverse Borel transform, A Borel of tau t as an integral 0 to infinity dz e to the minus z times this v of A of, so z is this one, and my omega was 1 over tau t, so it's basically z over tau t. That's the function that we are trying to do, and that's clearly a problem because we are meant to take the integral along the real axis, but we have a branch cut sitting right here. So the way that is suggested out is to say that, okay, really what it means, the Borel transform, or how we can generalize the Borel transform, is to say that, okay, we start at 0, and we're meant to sort of stop at infinity, but we can sort of generalize this by saying that we don't have to move along the real axis. You can actually sort of shake some contour in the complex plane such that we start at 0, end up at infinity, the 0 without imaginary value, but sort of do something in between. As long as the starting and the end point is 0 and infinity, that's a suitable generalization of what we do. And here, this is sort of a contour integral C that takes us from 0 to infinity. If we do this, we can integrate. We can do this integral. Okay? You can plug it in, you can do it numerically, but of course the answer you get then depends on the choice of the contour. Because in particular, if I do this versus something where I sort of do something and sort of end up from the other side, we'll have an ambiguity that a circle is cut once or twice or do something else. And this ambiguity means that my answer is not, strictly speaking, well defined. I'm out of time, but I will sort of just give you the punchline by sort of doing a simplification by saying that, okay, let me just briefly explain what happens, assuming that I didn't have a branch cut, but I had a single pole sitting on the complex. I have a single pole located at 3 over 2 tau pi t. Then the situation is similar in the sense that I can't do the integral on the positive real axis. There's an ambiguity on how often I sort of circle this pole as I sort of do my contour. And that means that I will pick up a residue from this pole here. So what I'll get is I get some piece that will just depend on tau t, that's the attractor if you want so. Plus you will get an ambiguity of circling the pole. You circle the pole, you take the residue of this. So you get e to the minus so you have z omega, where omega is this here, so you get e to the 3 tau t over tau pi t here, as you bring the tau t over to this, times the residue and elastic if you circle it once. So what you should sort of appreciate now is that this thing here, that is precisely the form of the dispersion relation when you plug in the non-hydro mode from the sort of linear analysis of this particular thing. So the ambiguity in the Borel transform precisely matches sort of this non-hydrodynamic mode decay times an sort of arbitrary sort of integration constant, which tells you that, okay, if you had initial conditions, you started out somewhere, then the system has to lose the memory of the initial conditions, and that's how it manifests itself in the inverse power transform.
Sorry, I missed. How did you get the two parts and where did the ambiguity go?
So the ambiguity is if I don't circle it at all,
Yeah.
then I don't get this. If I circulate once, I get one of these. If I circulate twice, then I get this with a factor 2 in the exponential. So I have the second sort of harmonic of the decay. But if I circulate just once, I get exactly sort of one of these sort of modes from the non-hydrodynamic mode decay that I would expect from the 2-point function of the theory.
How do I know that circulating one is the right choice?
Oh, there's no right choice. Basically, the way that you sort of are meant to sort of do it is to say that, okay, and I apologize, I had it here, but I'm really out of time. The correct way, as is argued in the sort of the research and literature, is to say that, okay, we have this ambiguity. Really what you should do is you should go back to our series here and say, it's not just a power series, it really is a trans series. So really sort of it works out in such a way that there's an n and an m, there's a coefficient, there's e to the minus whatever it is, m3 tau t over tau pi t, and then we have alpha n m over tau t to the m, such that at each entry of the trans series, so if m is 0, you just have the series I just discussed, which has this ambiguity. At the next level, you have an attractor for an attractor A1 for the one that's coming in with one of these factors here, and these two things have to match. I apologize, this is clearly not understandable from anybody who has not already sort of read the literature. Wait, maybe what I should do is I should simply sort of try to give you the reference for people to read this up, and then I will finish. Where is it? I know it was on one of my slides. Okay, this is not the right reference really, but it's sort of something that sort of gets you going. 13.2, 0697. This is Yannick Heller, and I'm probably mispronouncing his name, Bitashevsky. And with that, I finished for the day. And tomorrow, we'll try to sort of make applications to ion conditions. Thank you.